All right, so just to be sure everybody's in the right class, this is Theory of Computation, so CS3306. So if you're not in this, if you're not enrolled in this course, then probably you're in the wrong class. Okay, so all right, so so this course it's going to be a little different from I guess from the regular computer science course that you've been taking. So there won't be any there will be very little programming I guess implementation in this course. Okay, so it's more about logic and more about theoretical foundations of computation. Okay, right. But there's going to be a lot of, I guess you're going to be doing a lot of work, paperwork, right? In the sense that you'll be doing a lot of logic work using paper, not a programming language. Okay, and so I think you should be able to access the course on Blackboard. Are you able to access the course on Blackboard? No. Okay, so it might probably just actually should be able to. Okay, because I activated the course on the Blackboard course. So I think it might take a while to see that course. Okay, but the only thing that's on Blackboard right now is basically the syllabus and today's lecture. Okay, all right. So so I'm not going to kind of talk too much about what are the, I guess, the different topics in this course because I think like some of the terms and all, I mean, you might not really understand right now. Okay, so but very briefly I'll basically go through the syllabus, talk a little bit about the course logistics, the grading criteria and things like that, and then we can kind of talk a little bit about the introduction to this course. Okay, after we go through the syllabus. All right, so my name is Benjamin. So my office is N714. So so I have office hours Mondays and Wednesdays 1:30 to 3. I mean, if you have a class during that time, then you can email me and we can set up a different time. Okay, so the best way to contact me is through battery is low, I guess. The best way to contact me is through email, or you can send me a message through Blackboard. Okay, so that either way. So maybe probably the better way is through email. Okay, because I'm not always logged into Blackboard, right? So by email, I can see your email when you email it to me. Yeah, you can call me on my office number, but if it's like let's say 2 a.m. in the morning or say 7 a.m. in the morning, I won't be able to pick it up. Okay, right. So the best way is just email me, right? Okay, so learning objectives. I'm not gonna talk too much about this. Okay, so let's see. So the textbooks. Okay, so you should I think on the e-services, I think this is the textbooks that's listed, right? Okay. So, but I'll be also using some material from this particular book. Okay, so this is kind of a little older book, but this is also a very good reference. Okay, so I think you should be able to get the first book from the bookstore, and this one I think you can get it from Amazon or somewhere, right? Okay, if you're I'm not sure if there's a PDF version for this book online or somewhere, but that's the book that we're going to use. Okay. If you don't want to buy the book, if you just want to rent it, I think I got an email from somebody like from a bookstore that said they're willing to rent the book for like $50, $50. If you're interested, let me know. All right. Okay. So did you guys use this book in Digital Logic or something like that? No, not Digital Logic. Discrete Math? No. Okay. So I thought somebody told me you guys use the same book in Discrete Math, but I guess not. Okay. All right, so yeah, try to get a hold of these two books as soon as possible. All right. Okay, so now the topics are here. Okay, so so some of the initial topics like sets, order structure, you should have done in all the terms and things like that which are associated with sets. You should have done it in Discrete Math, right? So I'm not going to spend too much time talking about it, right? So then we'll talk about. I guess languages, grammars, right? How do you construct a particular language? Okay. Then we'll talk about finite automata. Then how do you construct a grammar for finite automata? Then we'll talk about context-free languages. Then finally, Turing machines and things like that. Okay. So yeah, but some of these terms you won't really I mean, it won't make a lot of sense to you, okay? But it's all about basically constructing languages so that a machine can recognize, okay? All right. And so I'll basically post everything on Blackboard, okay? So the PowerPoint slides and let's say assignments or notes or whatever, I'll put it on Blackboard. So or any kind of announcements or anything like that, I basically put it on Blackboard. And also, like if there is if I have to send a mass email or something, I'll just do it through Blackboard, okay? So at least you should at least check your Blackboard once a day, right? For this course, okay? All right. So the grading criteria, this is what you guys care about, right? You don't care about anything else, just the grading, right? so there's going to be assignments, right? Assignments 20%. There's going to be 2 midterms, 20%, final 25%, class participation 5%, and then there's going to be some in-class labs and quizzes. Okay, so 10%. Okay. All right. Fair enough. Okay, it's not like 100% for the final exam, right? Okay. That would be terrible. So again, so assignments, late submission. So you're expected to basically submit the assignments on or before the due date. So there will be a 15% deduction for every late day. Okay. All right, unless there is some, I guess, documented medical emergency or things like that. Exams. So again, right, no makeup exams unless there is some documented emergency, right? That you can provide. In-class activity, there are no makeups for in-class activity like labs and quizzes and things like that. But for the quizzes, I think I'll let you know, like, you know, like say at least a week or something before the quiz, okay? So that you just don't study day before the exam, right? So this is the labs and quizzes just to make sure you guys are at least, I guess, studying the material throughout the semester. Okay, so you can basically look up all this stuff on Blackboard. Okay, so all right, so let's see. Okay, any questions? No. All right, so usually like the first couple of weeks, the class is full, and maybe after 2 weeks, like probably half of you guys won't be coming. So I won't be surprised. But yeah, so what I'll be recording these lectures and then probably put them on. Probably through Dropbox or YouTube or something like that. Okay, that doesn't mean that you shouldn't show up in class. Okay, but anyway, all right. So let's just kind of start talking about automata theory. Okay, so let's see. So I put up the PDF file on Blackboard so that my PowerPoint, some of the images are missing. So I might have to kind of when I reach that slide which has a missing image, I might have to go back to the PDF file. Okay, but anyway. All right, so let's see. Let's just go here. All right, so today's slides are basically based on these two references. So chapter 1 of the book that I did. Chapter 1 of the book that we're going to use. The 2 books. Okay, so all the slides are basically adapted from chapter 1 from these 2 books. Okay. All right, so you might have to go back to basically look at those chapters, okay, later on. All right. Okay, so let's just kind of start talking about automata theory. Okay. Now, okay. So basically, this is all about studying about abstract machines. Okay, not like physical machines, but abstract machines. Okay. Now, if you want a machine to do something for you, right? You have to basically what? Give them some instructions, right? So the course is all about, okay, how do you basically construct a set of instructions for a particular machine? Okay, how do you define a particular language, right? So machines are kind of dumb, right? Unless you provide a very strict, well-defined set of instructions, right? Okay, so that's what we're going to learn in this course, okay? And also, so we'll be basically encountering these 2 topics a lot, okay? Computability and complexity. So we'll basically study, okay, given a particular problem, right? So let's say if you want to basically write an algorithm or create a machine to solve that problem. So first you need to analyze, okay, can that machine or the algorithm solve that problem? So that's basically computability, okay, right? And then complexity is all about, okay, let's say, okay, your algorithm or your machine can solve a particular problem, right? In principle, it can solve, but how long will it take for that machine or algorithm to solve the problem? That's complexity, okay? So if it's taking forever, right, to solve a particular problem, then you might want to find some approximation, right? Some approximate solution to that problem. Okay. All right. So there's gonna be different topics, right, which are associated with the study of automata theory. Okay. So we're gonna basically go through all of that. Now, so here, okay. So Alan Turing, right? So he's basically considered to be the founder of automata theory. Okay. So let me see. I missed the thing is missing over here. This picture is missing on a PowerPoint slide. So let me. Well, you guys can look up his picture, okay? So, all right. So now, so it all began with this guy Alan Turing. When he started studying this something called Turing machines, right? So he was basically interested in understanding, okay, given a particular problem, can you basically create a particular machine that can solve that problem in principle, okay? So he wanted to understand the boundaries between, okay, a problem which can be solved by a machine or not, okay? But in this course, what we're going to do is we're going to basically study Turing machine at the end, okay? But in reality, what it all began with Turing machines, okay? And then after Turing machine, there were some grammars, and people started studying grammars. People started studying finite automata and things like that, okay? But it all began with Turing machines. But in this course, we're going to basically kind of study Turing machine at the last, okay? Now, so this is basically the basic timeline, okay? So first Turing machines, right? So with a Turing machine, you will be basically able to analyze a particular problem, okay? In the sense that with a Turing machine, you'll be able to say, okay, can this particular problem be solved by a machine in principle, okay? So you should be able to tell, you should be able to decide if a problem can be solved by a machine or not using a Turing machine, okay? Then, so after Turing machine, then things like finite automata, which is like little bit, it's not as complicated as Turing machine, but people start studying finite automata, simpler version of Turing machines, okay? And then people start studying languages, like how do you formally define a language for a machine and things like that, okay? So we'll be basically studying all this, okay? And then after that, people start saying, okay, if I can build a machine that can solve a problem, but there are some problems which a machine can solve, but it takes forever, right? Okay, so people start saying, okay, if like things like NP-hard problems, right? So for those kind of problems, you have to come up with some approximate solution, okay? All right, and then finally, it all gave rise to compilers, modern computers, and things like that. Okay, so what we're going to do is basically the theory, or I guess the topic which basically precedes modern computers. Okay, all right. So basically, you should give credit to what Alan Turing, and not to, I guess, Steve Jobs or Bill Gates. Okay, so Alan Turing did all the hard work, and then they just use his theory to build computers, right? Okay, so okay, again, I said, right, so there's going to be two main things, okay, that you're gonna encounter in this course. There's computability and complexity. Okay, so so again, as I mentioned before, right, so what we're going to do is, okay, given a particular problem, right, we're gonna build certain simple, I guess, abstract machines, okay, on paper. So using those abstract machines on paper, we'll be able to decide, okay, can this machine solve this particular problem? Okay, in principle, okay. So we won't be building electronic circuits and things like that, okay, but just abstract machines that we're going to build, and we're going to, okay, using the abstract machine, we can decide, okay, if this machine can solve this problem or not, okay, all right. So you won't be writing any C++ program or Java or anything like that, okay, in this course. All right, then complexity is this, okay, so so let's say you come up with some kind of machine, right, that can solve a problem. Now the question is, okay, how long does it take? What is the complexity of the solution, right? So does it take? I mean, can the problem be solved in polynomial time? Does it take exponential time to solve the problem? Things like that, right? So with this abstract machines, right, you'll be able to decide, okay, how long will it take for that problem to be solved by the machine? Okay. So if it's taking too long, then you might want to come up with some approximate solution, like greedy algorithms or approximation algorithms, right? Okay. Okay. So let's see. So I want to kind of give you a very brief introduction to finite automata. Okay, so nothing technical, but just simple things. Okay, so let me go back to my PDF file. So it's because some of the images are basically missing here. So okay, hang on. All right, so okay, so so finite automata. This is not the next topic, but it's probably maybe we'll start talking about in detail about finite automata in the next probably 2 to 3 weeks. Okay. Now, so finite automata is simply it has basically a finite set of states. Okay, that can basically allow you to tell it can basically accept or reject certain strings. So this string is going to be I guess the set of instructions that you provide to the machine. Okay. Right, but this is very simple definition, but we're gonna go more in detail later on. Okay, but this is to give you just a snapshot of what's coming up. Okay, okay. So now you'll be making this diagrams a lot. Okay, in this course, this kind of diagrams a lot. Okay, so let's say if you want to represent this a machine that can perform on off switch, right? So what you're gonna come up with is, okay, the machine will have 2 different states. Okay, on off, right? And there's going to be some kind of action involved, right? So if you click the on switch, right? If you click on, it's going to go up. So let's say for example, let's say if the machine is at the off state, right? So so now you can push something, right? Some kind of button in your machine, and it will basically go to the on state, right? And then you push some switch in your machine, then you're going to go to the off state. Okay. So this is at a, I mean, the description is at a very high level, right? We're not talking about, okay, binary circuits and things like that, right? Okay. And for example, say, another example is this, right? Let's say if you want to come up with some algorithm, or you want to come up with some kind of machine, right, that can recognize the word then, right? THEN. Okay. So there's going to be this many states, right? So you're going to have the start state, and you're going to have 1, 2, 3, 4 other states, right? And this is basically the final state. Okay. So now you can see, okay, so you can basically, so if you're given any word, right, you can basically simply feed that word to this machine, right? And once you're done reading this word, you should end up at the final state, right? So that means the machine can recognize this word. If you end up somewhere, let's say if you end up somewhere here and you cannot move forward, that's not I guess, feasible machine. Okay. So you'll be coming up with this kind of, so you'll be basically making all this kind of diagrams, okay, to solve a particular problem, okay, throughout this course, okay. So you cannot just say, you cannot make like you cannot make a loop or something like that, right? Because you will never be able to reach the final state, okay. Or something, if you build a machine and then if it stops before you reach the final state, right? That's not a feasible machine, right? Okay, that's not the correct solution to the problem, right? Okay, so okay, so let's keep going. Let me go back to my PowerPoint. Okay, all right. So now the applications, right? So the application of finite automata, right? So I mean, this is going to be very vague, okay? But just bear with me, okay? Now, so the theory of computation, right? So this is going to be more useful, I guess. This is going to be more useful if you're going to like things like compilers, designing languages and things like that. Okay. But if you're going probably into, let's say, data analytics or things like, maybe it might not be very. I mean, you might not use it a lot. Okay. But if you're going to like designing compilers, or even like higher software design, things like so you're going to use some of these things that we discussed in this course. Okay. All right. So, all right. So yeah, personally for me, like my area is like data analytics. So I don't get to use a lot of the stuff that's a lot of the topics in this particular, I guess, in this particular field. Okay, but it certainly is useful. Okay. So now. So the concept of finite automata, or I guess in general concept of theory of computation, right? So if you're doing any kind of software, right? If you're doing any kind of software design, okay, just to basically solve a particular problem, so you're going to need some concept from theory of computation, especially if you're doing, say, software analysis, right? Things like, okay, is this software correct? Is this what's the complexity of the software, right? How long does it take for the software to solve a problem, things like that. Okay. And then especially also when you're building compilers, okay. So when you're building compilers, you'll be needing a lot of concept from theory of computation, because you'll be so for example something like this, right? The image that we just saw. Let me go back here. So it's here, right? So let's say, remember machines, right? So you have to break the instructions down to the I guess the smallest bit possible, right? When you give a set of instructions to a machine, right? So in compiler, so you have to break your whatever the language that you have into smaller components, okay? So you'll be basically doing all this kind of, so you'll be generating all this kind of diagrams, right? In the form of finite automata, right? And see, okay, is my design, right? Is my design accurate or not? So you'll be doing all of that. So you're gonna need some concepts from theory of computation, okay? Now, so two things, right? So software analysis and compiler design, okay? So those are two main things that requires application from theory of computation, okay? All right, so all right. Now, okay, formal approach. Okay, so let's see. So in discrete math, do you guys do any like formal proofs when you took discrete maths? What do you do? Was that? Any? What was that? Right? What? No. Do you do anything like formal proofs or something like that? Like say you given a particular statement, like conditional statement. If something is true, then this is true. You did it, right? Yes. Okay. So what kind of formal truth do you do? Was that? I know, but like the techniques that you use, like from some, was that? Truth table, okay. Do you do like proof by induction, things like that? Proof by contradiction, things like that. Okay, so yeah, so that's what it's all about. Okay, so remember, so later on, remember that one of the main things that I mentioned, right? So what you're going to be doing is you're going to say, okay, if once I have a finite automata, or I guess an abstract machine, right? So you're going to ask the question, okay, can I solve this problem with this particular machine, right? Okay, so you're going to need some kind of formal proof, okay, later on, okay. So some of the techniques that you use in discrete math, right? So you're gonna need some of those techniques later on, okay, to prove that your solution is correct, okay. Now, so what we're gonna do is kind of at least today I want to do is kind of go through some of the techniques, okay. I guess kind of just a refresher for you guys, right, and look at some problems. So again, right, so let's say you come up with a solution, right, some kind of abstract machine to solve a problem, right. Now, so in software design, you have something called testing, right? So you can basically you can basically come up with some simple test cases, right? So you can say, okay, I have 3 or 4 examples. I want to say, okay, then you just feed your test cases to your solution or your algorithm, and if the answer is correct to the expected results, right, then okay, I have a valid solution, right? Now, when it gets more and more complicated, right? So you can't basically test your solution to every possible case, right? You can't do that. So you have to come up with some kind of formal proof. Okay, is my solution correct? So you have to come up with some kind of formal proof. Okay, so that's why formal proof is necessary. Okay, if it's a simple algorithm, right, you can simply kind of test, right? Test with a few test cases, right? All right. So, but it gets more and more complicated. You have to come with some formal proof, right? All right. Okay, so that's why. If you thought like you don't need discrete math when you're taking discrete math, then maybe you might you should rethink, right? Okay. All right. So okay. So let's. So what I want to do is kind of go through some of the techniques. Okay. So most of the time, so you guys have seen all of this before, right? So just some few definitions, okay, before we talk about the proof techniques, okay. So most of the time, what you're going to encounter is some kind of statement, right? Let's say if A is true, right, then B is true, something like that, right? So you prove that statement. Provided A is true, then show that B is true, or something like some kind of statement, right? So you have so simple English statements mixed with, I guess, some math symbols, right? Okay. So you guys have done like sets and stuff like that, right? The symbols and the notations involved with sets, right? Okay. So you'll encounter some of the symbols here too, right? Now, so let's just kind of go through all this. Okay. So just some basic definition, right? So here, hang on, let me. It's over here. Okay. So let's say you have two statements, right? A and B, right? Okay. So not A is simply the negation, right? A and B is simply a conjunction. A or B is simply disjunctions, right? I mean, you've basically done the truth tables for all this kind of stuff, right, before. So I'm not going to go through that again. Okay. Now, so most of the time, this is what we're going to be doing. Okay. The statements that we're going to basically the kind of statement that we're going to prove a lot is basically a conditional statement. Okay, which means if A, then B, right? So if A is true, then B is true, right? So you can now instead of saying if A then B, then you can also say A implies B, right? Okay, so this is simply a conditional statement, right? There are some terms associated with this particular statement, right? So A is basically the antecedent and B is a consequent, right? Or you can say A is the so some people say A is basically the hypothesis and B is basically the conclusion. Okay, something like that. So different terms, right? So that means if you study like something like say if someone makes an assertion like say if you study at least 4 hours a day for this course, then you'll get an A or something like that. That's an assertion, right? Okay. So basically that means to get an A, you have to study 4 hours, right? Something like that. Okay. Okay. So let's hang on. So there's a table missing here, but let me just pull this up. Hang on. Yeah. Sorry. The image is missing here. I wanted to show you some image over here, but sorry. Okay, so this is a slide. Okay, so let me just talk a little bit about this. Okay, now, okay, so here's a statement: if A then B, right? Okay, here's an assertion, right? Now, so you can make a contrapositive assertion. Okay, so let's say given if A then B, that's an assertion, right? The contrapositive assertion is this: if not B, then not A. Okay. So given an assertion, something like this, right? If A then B, the contrapositive assertion is if not B, then not A. Okay. Now, okay, so now we'll be basically later on one of the techniques that we're going to look at is, let's say if you want to prove this is true, right? This assertion is true. It's basically sufficient to prove the contrapositive assertion is true, or the contrapositive statement is true. Okay. Now, so let's look at this. Okay. So let's try to understand the truth table for this statement, for this conditional statement. Okay. If A then B, right? And then so yeah, we can basically look at both. Okay. The truth table for if A then B and the contrapositive statement, right? Which is if not B then not A. Okay. So do you guys do this truth table condition in your discrete math? Okay, you did, right? So let's see. So so again, right? So you have two statements A and B, right? So basically we basically list out all the possible values, right? So A is true, B is true, A is true, B is false, A is false, B is true, then A is false, B is false, right? Now, so let's look at this first, okay? So we have true, false, true, true. Okay, so let's see. Now, so let's go back to the examples. Let's say if I make an assertion, if you study at least 4 hours a day on this course, then you get an A. Okay, so that's basically this assertion. That's the assertion, right? So A is simply okay, study 4 hours, at least 4 hours. B is what? Getting an A, right? Now, So now in the first case, when you study at least 4 hours, right, a day, and you get an A, right? You also get an A. You study 4 hours, you also get an A, right? So that means my assertion is true, right? So I haven't basically violated my assertion, right? That's true, right? Now how about this one right here? That means you studied at least 4 hours a day, and then you don't get an A, right? Okay, you're supposed to get an A, but you don't get an A, right? So that means, so that basically violates my assertion, right? So this is basically false. Okay. Now how about this one right here? So that means you didn't study 4 hours, right? But you got an A, right? You didn't study 4 hours, but you got an A, right? So why is that assertion still true? Be there in discriminant. So let's say my assertion is if you study at least 4 hours a day, you get an A, right? That's my assertion, right? But what happened is you didn't study for at least 4 hours, but you got an A, right? So why is that, if this conditional, that whatever assertion is still true? And just the logic, I guess. What's that?
The A doesn't even apply here.
What's that?
Because the A doesn't even apply here.
Yeah, so my assertion was, okay, if you study at least 4 hours, you're gonna get an A, right? I didn't say anything about if you didn't study, right? Okay, so it doesn't apply to those people who don't study at least like 4 hours, right? Okay, so my assertion is still true. I haven't violated my assertion, right? Okay, so all right, so now how about this one right here? Again, same thing, right? So my assertion only applies to if you study at least 4 hours, right? Okay. Now how about this one? So this might, so now this one, so remember, it's not the contrapositive, right? It's not, remember, it's B and A are kind of switched around, right? So it's if not B, then not A. Okay, it's not if not A, then not B. Okay, so B comes before, right? Now I'm gonna leave you guys to think about this, okay? But the point I want to make over here is this, okay? So if you look at the truth table, right? So the truth table for this conditional statement and its contrapositive statement, right? It's basically the same. Okay. So the only case when they're false is this case, right? When A is true and B is false, right? Okay. So that's the only case when they are when they are false. Okay. The remaining cases, they are all true. Okay. So we later on we'll see that. Okay. Let's say given let's say if you're asked to prove this statement, right? If A, then B, right? So it would basically be enough. So it would basically be enough to basically prove the contrapositive statement. So maybe at some situation it might be easier for you to prove this the contrapositive than the actual statement. Okay. All right. So let's see, what time is it? Okay, good. So we're gonna look at some proof techniques. Okay. So I mean, some of the symbols that we're gonna use are integers, odd integers. I don't have to explain to you what is even, odd integers, right? Okay, so if you don't know what odd even, then maybe, I don't know, talk to me or talk to somebody. Okay, so again, so here, so this notation over here, M vertical line, and so we'll basically read this as M perfectly divides N. Okay, so we'll use this notation. Okay. So prime numbers, right? So how do you define a prime number, things like that? Okay, so we'll be using some of the notation later on. Okay. Okay, one more thing. So again, so if you have an odd integer, right? So you can basically express that odd integer in this format, right? 2 times k plus 1, right? Where k is some integer, right? So if it's even, you can express that number in terms of 2 times k, right? So we'll be using some of this right later on. Okay. Now, so let's go to our PowerPoint. Sorry, I'm kind of switching back between. So let me just go over here. So again, just some notations. Okay, so So let's say, for example, if you say if H then C, right? You can. There are different ways of saying, right? So let's say you can say this statement as H implies C, or you can write in this way, right? H implies C, C if H. Different ways of saying it, okay? But most of the time we'll just use this statement or this or this, okay? All right. Okay, so now the first technique that you can use is simply if you want to prove a particular statement is true, right, you can simply do exhaustive checking, okay? Or this is called the brute force method, right, where you basically check every single possibility, okay? All right. So a lot of times, yeah, if the problem is not very big, right, then you can use this technique, but a lot of times this is not very useful, okay, because the solution space is so big that you can't just use this exhaustive checking, okay? All right. So now, so for example, say so if somebody makes a statement, okay, there is a prime number between 200 and 220, right? So what you can do, you can simply check every single possibility, right? Between them. It's not, there are only 20 numbers, right? You can check them, right? Easily, right? Okay. So let's say if somebody makes a statement, each of the numbers 288 this is divisible by 9, right? So again, you can simply check, right? Okay. So I mean, again, depending on the problem, you don't have to. So let's say, yeah, the statement is simple, right? So you can simply do exhaustive checking, right? So you don't have to kind of, I don't know, spend hours trying to come up with some kind of formula, right? Okay. Okay. So conditional proof. Okay. So let's just hang on. Okay. So all right. So so one of the techniques that you can basically use is to basically prove a conditional statement is true is something by starting by assuming that the antecedent is true. So let's say if I say, okay, here's an example. Let's say if X is odd and Y is even, then X minus Y is odd, right? So basically the hypothesis, or I guess the antecedent is simply what X is odd and Y is even, right? So you basically you start with that, okay, and then you simply kind of do a series of derivations until you reach the consequent statement. Okay. So let's say here, okay, so if I want to prove, if somebody wants to prove, okay, if X is odd and Y is even, then X minus Y is odd. So okay, now, okay, before we go there, so now okay, so this statement, so as a computer science person, right, so you might not be able to connect to this kind of statements, okay, but let's say, for example, say let's say you're given a particular problem, right, and then you come up with a solution to that problem, and let's say the solution is basically polynomial time, in the sense that the algorithm that you come up can solve the problem in polynomial time, okay, something like that. Now you might have another problem, right? Okay. Now you can basically say, if somebody asks you, say, okay, if this solution is polynomial time, then show that this particular solution is also polynomial time, something like that. Okay. So I mean, you might not be able. I mean, as a computer science person, you might not be able to really connect with this statement, right? Okay, but something like, say, okay, if you have a solution which is polynomial time, can I basically prove that another solution to a different problem is also polynomial time, something like that? Okay. But let's just kind of use this very simple example, right, to illustrate this I guess these techniques. Okay. Now, so what you can do is you can simply assume, right, the antecedent is true, right? So let's say assume that X is odd and Y is even, right? Okay. So now what do you do? So you can basically express X and Y, right, in terms of two different integers, right? So if X is odd, you can express X as 2 times K plus 1, right? And then Y you can express as 2 times M, right? Okay, now, so what we need to do is X minus Y is odd, right? So what do? You express X minus Y in terms of this, right? Okay. This is 2K plus 1 and 2 times M, right? Okay. Then so here you can simply, so now you can simply expand this in terms of what? 2 times some integer plus 1, right? Because you want to show X minus Y is basically odd, right? All right. So here X minus Y is simply 2 of K minus M plus 1, right? So Now, so k and m are integers, so k minus m is integer, right? So since you can express this as 2 times an integer plus 1, x minus y is odd, right? Okay. Now, yeah, so from here to here is simply basic algebra, right? Okay. Now again, so if x is odd, then x squared is odd, right? All right. So again, same thing. You simply assume x is odd, right? Okay. Then you express x in terms of what? 2 times k plus 1, right? And then from there you can say, okay, you can express x squared, right? So get square, all the simple algebra, right? Then you get something like this. So this is an integer, right? So 2 times integer plus 1, right? So that's my x squared is odd, right? So basically, so the technique here is, okay, you simply start by assuming that the antecedent is true, okay? So let's just assume that whatever hypothesis you have is true, right? And then from there you kind of, I guess, do a series of derivations, right? Okay, and then until you reach the consequent, right? Until you reach the consequent statement, okay? All right. Okay. Now, so on more example, right? So again, same thing right here. So so if x is even, then x squared is even. So you can do this, right? All right. So assume x is even, and express x as what? 2 times k, and get x squared. Okay, all of that. You can do that, right? Class, do a 1-minute quiz. Okay, we won't do 1-minute quiz. Let's keep going. Okay. All right. So, okay. So I have the image, the truth table missing over here. Okay, but so what we're gonna do is here are 2 examples where you're gonna prove the original, I guess, statement, the conditional statement, by proving the contrapositive statement is true. Okay. So let's say, for example, here, if I say if x squared is odd, then x is odd. So if you want to prove this statement, right? So what is the contrapositive? So you basically switch a and b, right? So the contrapositive, if x is even, right? Remember not, okay? So that's why you have even over here, okay? So if x is even, then x squared is even. So but we basically proved this, right, in the previous slide, right? So let's say if I ask you if x squared is odd, then x is odd, right? So it might so it's going to be a little harder for you to kind of use the technique that we just discussed in the previous slide. So if you simply assume x squared is odd, then it might be hard to go come to this conclusion, right? So what you can do is you can get the contrapositive statement and prove that contrapositive statement, okay? So it's basically easier to prove the contrapositive statement, right, than proving the direct statement, right? So you have to kind of try different ways of proving the statement, okay? All right. So you might have to kind of bang your head a little bit trying to prove the statement, right? So now again, same thing here. If you have to prove if x squared is even, then x is even, right? So again, so it might be hard for you to kind of start off with the antecedent, right? So let's say, okay, then you take the contrapositive and say, okay, can I prove that contrapositive statement, right? Easier, okay. All right, so now, okay, so here again, if and only if proofs, okay. So let's, for example, here the conditional statement is what? If A then B, right? So that means A implies B, right? It doesn't say anything about B implies A, right? Okay. So with if and only if is simply saying, okay, if I say a statement, okay, A if and only if B, right? So that means what? A implies B and B implies A, right? So you have to basically prove both ways, right? Okay. So if you're given a statement and say, okay, prove if A if and only if B, right? So you have to show A implies B and B implies A, right? So you can prove those 2 different statements, or what you can do is you can simply, I guess, create a series of if and only if statements. Okay. So what I mean by that, let's look at a simple example. Okay. So here, here's an example. So let's say if x is even, so x is even. So if somebody makes a statement, if x is even, if and only if x squared minus 2 times x plus 1 is odd. Okay, so you have to basically show if x is even, right? This is what? This is odd, right? You have to show that. And then also you have to show, okay, if this x squared minus 2 times x plus 1 is odd, x is even, right? Okay, so that's one way. Or what you can do is you can simply, I guess, make a series of if and only if statements, okay? Until you reach the statement that you want to prove. Okay, so let's say, so here's a simple example. Let's say here. So you start with saying x even if and only if x equals 2 times k, okay? By definition, right? X is even, so I'm going to simply start out with this particular statement, okay? X is even if and only if x equals 2 times k, right? For some integer k, okay? That's definition, right? Now, so that means, so by simple algebra, so you can say if and only if x minus 1 equals 2 times of k minus 1, right? Okay. So again, so what we're doing is kind of making a series of if and only if statements, okay? Start with this, go over here, right? Times 1050, okay. This class ends at 11:15, right? Okay. All right. Then you keep on expanding, right? If and only if, right? Okay. So the goal is to basically reach. So remember, the goal is what? To show that this is what? Odd, right? So so at the end you might want to express this in terms of what? 2 times some integer plus 1, something like that, right? Okay. So that's what we're trying to achieve. Okay. So so then if and only if x minus 1 is odd, right? If and only x minus 1 squared is odd. So this one we proved this before, right? Example for instance in the previous slide. Okay. Then you expand this. Okay. So it's basically just a series of if and only statements until you kind of, so you have to kind of think of I guess a path, right? That can allow you to go from here to here, right? Okay. Okay. All right. So yeah. So I mean, most of these topics, right, is basically they originate from people who are working in I guess people who are working in mathematics, right? Probably not direct computer science, right? Okay. All right. So okay. So now proof by contradiction. Okay. So this is also another popular topic. Okay. So in this case, what do you do? Proof by contradiction. So what do you mean by proof by contradiction? Let's hear from you guys. I just don't want to talk all the time. I want you guys to talk. So so you guys did proof by contradiction, right? In discrete math, right? So what is that? You see, I don't want you to read from there. Let me just put it. So let's say if I say if I make a statement, if A is true, then B is true, something like that, right? So so if you want to prove that by contradiction, so what is that? What's that?
You basically just prove it false.
So you start with A, you assume that A is not true, right? And then you come up with some contradictory statement, right? Something like that, right? Okay. So okay. So let's look at some example. Okay. So let's say if I want to so let's look at some example. So if x squared is odd and then x is odd, right? Okay. So that's if x squared is odd, then x is odd, right? So assume the x squared is odd and x is even. Okay. So that means, so you're saying, okay, I'm going to assume this is odd and this is what? So I'm going to assume the antecedent is true, but the consequence is what? False, right? Okay. So that's what I'm doing over here. Okay. So if x squared is odd, then x is odd. So, but what I'm doing is I'm simply going to assume x squared is odd, but I'm also going to assume that x is even. Okay. All right. Then then what you can do is you can express x equals 2 times k, right? Okay. Then so what we have over here is this, right? So now since we assume x is even, right? So now you can say x squared is what? This, right? Then you can simply expand it, and so what you want to do is basically come up with some statement which is contradictory to the antecedent, right? Okay. So here, so what we ended over here is this, right? So what we ended over here is x squared equals what? 2 times k squared, right? So this simply shows that x squared is what? This means x squared is basically even, right? Which is not true, which is contradictory to the antecedent, right? Okay. So again, so again, just a summary, right? So what we do is you simply assume that the consequence is false, right? Okay, and then simply do a series of derivations to come to a statement which is contradictory to what? To the antecedent. Okay, all right. Okay, so now let's see again. So here I'm making a statement over here, right? So if the number 2 can perfectly divide 5 times n, then n is even. Okay, so what do you do here? How do you start? So if you want to prove this by contradiction, what do you do? So you assume n is odd, right? Then what you gotta do is, okay, let's say you assume if this is true and then n is odd, right? Then now since n is odd, and since 2 can perfectly divide 5 times n, right? So you can write 5 times n in terms of 2 times d, right? Because 5 times n is perfectly divisible by 2, right? So you can express this in terms of 2 times d, right? Okay. And then since n is odd, you can write x. This is what you assume, right? N is odd. You can write n equals 2 times k plus 1, right? So then what we have is, so you can do this derivative. 2 times d can be expressed as what? 5 times n, right? Because 2 can perfectly divide 5 times n, right? Then you then you express n in terms of 2k plus 1, which is n is what? You assume n is odd, right? Okay, so then you have simple algebra. You have 10 times k plus 5, right? And then if you solve for 5, what do you get? 2 times d minus 5k, right? What is that? 5 is even. That cannot be true, right? A contradiction. Okay. Okay. All right. So you have to, so you have to read some kind of contradictory statement, right? Okay. Now, so you guys are not used to all this stuff, right? No, like you don't do. As a computer science guy, you don't do this often, right? On a regular basis, you're just writing code, right? So you might have to kind of get used to it a little bit, okay? After this course, you can forget about it. At least during this course, maybe get used to it, right? But it'll be helpful later on, okay? Okay, so now, so let's see what then. So what we're going to do is kind of go through some preliminary concepts, okay? That would allow us to kind of start talking about finite automata and things like that. Okay, so we have to go through some basic definitions and terms, things like that. Okay, now, so I'm not going to go through sets and things like that. Okay, so I'm going to skip all this stuff. You can read this later on. So like sets and the different operations on sets, right? So I'm not going to go through that, but so I'm going to start talking from alphabet. Okay. All right. So what we're going to do later on is say remember. So when we're talking about machine, right? So if you want to give a set of instructions, right, to a machine, right, you need to have some kind of language, right, grammar and things like that, right? But the basic unit is basically alphabet. Okay. What constitutes the alphabet, right? That allow you to make up the language and the grammars, right, that a machine can recognize. Okay. So alphabet, so the notation that we're going to use is either sigma or uppercase A, okay? So it was simply, so alphabet is simply a finite non-empty set of symbols, right? That you can use to build your language or a grammar for a particular machine, okay? So, so you can come up with simple alphabet, let's say 0, 1, right? So that's an alphabet, right? So using 0 and 1, you can come up with any kind of language, okay? Or a string or anything like that. Okay, by using different combinations of 0 and 1, right? Okay. We don't speak in binary, so that's not our alphabet. Now, so you can do or you can say, okay, I want to build a language that only use lower cases. Okay, so that's one alphabet, right? So numeric, so you can do lowercase a to z, uppercase a to z, or say numbers 0 to 9, right? Okay. So I guess you can see, okay, if yeah, so it might seem okay if once you increase the number of characters in alphabet, right? So you probably can make more and more complex languages, right? Now, so DNA molecule, so you can have 4 different characters, A, C, G, T, right? I mean, but it's very powerful. I mean, even if you have 4 different characters, right, you can basically come up with a very complicated language, right? Like a DNA molecule, right? Okay. So even with 0, 1, you can come up with some a complicated language, right? Okay, so yeah, the problem comes when to decipher. I mean, to decipher the language, right? That's the hard part. Okay, but with simple alphabets, you can come up with pretty powerful language. Okay, so this is what I'm talking about. Okay, so here now, so let's say you have an alphabet, right, with some characters. Okay, so you can do all kinds of operations on that set, right? Or I guess alphabet set. For example, here, right? So if you simply write, okay, sigma to the power k, right? What is that? It's simply the set of all the strings, right? I guess all the strings that can be made up by the characters in the alphabet, right? But the length of the string has to be what? K. Okay. Okay. So if I simply write, say, something like, say, if I take this example over here, right? Sigma 0, 1, and if I say sigma something like this, right? So that means what? So so you have to come up with all the strings consisting of those characters in the alphabet, right? But the length of the string has to be 2. Okay. So like 0, 0, 0, 1, 1, 1, 1, 0, things like that. Okay. Now, so you can also do this too, right? So sigma with asterisk, right? So that's simply, so this becomes a little more complicated, right? So what you do is you first come up with the I guess the set of all the, I guess, so this will be simply the empty set, okay? Because you're not putting anything here, right? Then you have all the strings, right? Which has only one character from the alphabet, right? Okay, then this is simply what? All the strings with 2 characters, right? And then you can keep on expanding, right? So if you take the union of all of that, right? So that's simply denoted by this, okay? Okay, sigma asterisk, okay. So we'll be kind of using this notation, okay? Referring to this kind of notation quite often later on, okay? Or you can do this. So sigma plus, right? So this is simply the same thing except that you don't have the empty set. Okay, so you basically take you basically, given an alphabet, right? Alphabet, so you create all the possible strings with at most, I guess, with exactly one character, right? Then you create all the strings with what? Exactly 2 characters in the alphabet. Okay, then we exactly what? 3 different characters, and then you basically take the union, right, of all of them. Okay. So the strings can be of length 1, length 2, length 3, right? Length 4, whatever, right? Keeps going. Okay. So okay. So we'll be referring to this this kind of notation quite often. Okay. So let's see. So we have some time here. Now, okay. Now let me go to the PDF one. So I have the picture missing here. Let's see. So again, some notations for the string for sets, right? So you guys done all the notation, right? Okay. You did it on discrete man, right? So yeah. So you might. So we have to kind of. So we'll be using some of the notations. Okay. So if you, yeah, it'd be good to kind of just kind of refresh some of this. Okay. Okay. So let's keep going. Okay. Okay. So again, so these are kind of straightforward topics. Okay. So strings, right? So given an alphabet, right, you can basically create strings out of the alphabet, right? Okay. So for example, here, maximize this a little bit. So here, sorry. So here's an alphabet, right? With only two different characters, A and B, right? Okay. Some of the strings are what? So some of the string that you can create with alphabet with this particular alphabet is what? You can create A, A or B. So you can combine AA, right? AA, or I guess AB, BA, BB, AA, BB, right? Okay. So you simply combine. I guess you simply combine or concatenate the different characters in your alphabet, right? Okay. So now, or you can say that the empty string is simply okay. You can also have an empty string, which is simply denoted by this. Okay. So we'll be using this. We'll be using this notation a lot. Okay. Empty string. I mean, maybe different book might use a different notation, but we'll just take this notation as the empty string. Okay. Now, so let's say, for example, here, right? So if you concatenate two strings, right? You simply put one after another, right? That's the definition, right? So if you concatenate AB and BAB, what do you do? You have AB, BAB, right? Okay. So you can realize, right? So you can make all these different strings, right? By different combinations of the characters in alphabet, right? Okay. So let's say this might mean something, right? So let's say AB might mean something, right? To a machine, right? Your machine reads it, okay, one by one. BAB might mean something, right? Or I guess AB, BAB might mean something, right? Okay. So again, some definitions, right? So let's say if you concatenate a string with an empty string, right? Or I guess if you concatenate an empty string with a string, you get the string, right? Okay. All right. Now here, so we're just going through some definitions. Okay. So now, if let's say you have a string, right? S. Okay. S is simply a string which you create out of a particular alphabet, right? Let's say, for example, so let's say you're given this alphabet, right? Then you have a string, right? S. Okay. Now S can be it can be of any length, right? It can be length 1, length 2, length 3, whatever, right? Now, so when somebody writes S to the power n, right? Okay, so we'll be kind of using this notation quite often. Okay, if someone writes S to the power n, it simply denotes the concatenation of S with itself n times. Okay. So now okay, so remember, so S to the power 0 that means it's empty. That means you're not doing anything, right? So this one is empty string. Okay. Now, so remember, so S. So let's say S is. So here, for example, you have AB3, right? So that means what? So you basically concatenate AB 3 times, right, by itself. Okay. So you have AB, AB, AB. Okay. All right. Okay. So let's see. Now, so languages. Okay. So now we'll basically discuss languages more in detail. Okay, later on. Okay. But this is kind of just a snapshot of what languages, right? So you have alphabet, right? And then strings, or I guess strings would be words, right? And then with strings or with words, you can basically create languages, right? Okay. So first you have to know the alphabet, right? Then you try to create simple words or strings, and then with the strings you can create some language. Okay. Now now remember, you cannot simply mix words and make a language, right? There has to be some grammar. Okay. So we'll discuss grammar later on. Okay. But language simply is just a set of strings, right? Like for example, English, where you cannot just randomly select words and make a language, right? You won't understand, right? Machine won't understand. So you have to follow certain rules, right? Grammars, which we'll discuss, start discussing in the next class. Okay. So, but in general, it's simply, I guess, a collection of strings, right? A collection of words, right? Okay. So, so here, so let's discuss something. Now, okay. So we already discussed the notation, right? So that's it. So some examples, right? Some examples of language. So let's say you're given a particular alphabet A, okay? Now, some examples of languages that you can create out of A is what? So let's say you get an empty set, right? It's like, I don't know, you don't speak to each. You have everything, but you don't speak to each other. Right? Just, I don't know. Okay, you just don't talk, right? Then, or you can have the empty string. Okay, so this also, I mean, so we'll discuss a little difference, okay, between this and this, and I'll show you some example, okay, where the difference between empty set and then language with empty string. Okay. So I'll show you some example where the difference becomes very eminent. Okay. Then, or you can simply have A itself. This would be simply the characters, right? Itself. Okay. So you're not making any you're not making any I guess any strings or words out of it, right? Now, how about this one? This is when you start making, you started combining the characters, right, in the alphabet, right? Okay. Now, so another example is this. So let's say if I wanna make a language using this given alphabet. So here we're gonna use A is what? A is to be A, B. Okay. All right. So now what you can so I can define a language that basically looks like this. Okay. So A, B to the power N, A, right? So that means what? So that means all the words, right? All the words in that language should begin with what? Begin with A, end with A, right? But in between what you can have as many B as you want, right? So you can have you can have 0 B's, 1 B's, 2 B's, right? Okay. So here, so you can say, okay, so A, right? So you start with A and end with A, right? But there's no B, right? So you have A, B, A, where you have only one B, right? And A, B, B, A, B, B, A, right? So I mean, so this is, I guess, so this notation over here, right, is basically a short way of writing, right, this language, right? Okay, so this is simply a set, right? A set of all the strings, right? That basically looks like this, right? Okay, so remember A, B, A, right? They basically the characters, right, in the alphabet, the given alphabet, right? Okay. Now this is one example, right? So you can come with different different examples, right? So it's something like, say, maybe instead of A, B, and A, you can have, say, B, A to the power N, B, or something like that, right? Okay. So I guess the basic idea is you should be able to comfortable. I guess you should be comfortable describing languages in this format. Okay. So that means if I say A, B, B to the power N, A, so you should be able to understand what this language is, right? Okay. So what we'll be doing is, let's say I come up with this particular language, right? And I say, and I give you some kind of machine, right? So I'm going to ask a question. Okay, can the machine recognize this particular language, something like that? Okay, so we'll be doing this stuff later on. Okay. All right. Or I guess if I have a machine, right, and then I say come up with a particular language that the machine can recognize, something like that. Okay. So yeah, at least the notation, right? So you should be comfortable writing language in this format, okay? Or I guess, or if somebody writes a language in this format, you should be able to understand what this means, right? Now, let's see, what time is it? Okay, so now let's see. Okay, I'm missing some images over here. Let me see. So let's see. We have a few more slides, and then we might have to finish this later on. But let me. Okay, so let's just go over here. Okay, so I have this images missing, but let's go through this. Okay, so language operations. Okay. So there are different so you can basically combine language, okay, using certain operations. So the most probably the useful and widely used is basically the product. Okay, so let's say now I have two different languages, like L and M, right? Okay, so each of them have some definition, right? Now you can basically define the product of these two languages by this notation: LM equals ST. It's not, so this is you're simply concatenating S and T, okay? Now S will be what? S will belong to L, and T will belong to M. Okay, so that means, so remember, LM is basically the product of LM, but this is also a language, right? So in this language, the language basically consists of all these words in such a way that S, right? S belongs to what? S comes from L, and T comes from M. Okay, so remember, so remember, this is for every S, right? In the every word or string in language L, okay? And then this is for what? T is what? Every string or word that belongs to M, right? So you can imagine there's going to be different combinations, right? Okay, so let's say if you pick one word from language L, right? Then what you can do, you can concatenate all the words or string from language M, right? So you can basically repeat the same process, right? Okay. All right. So now, so some notation again. So if you have a language L, right? L to the power 0 is basically empty. Okay, empty set. And L to the power n, right, is what? Now remember, we defined this. Okay, L to the power n. So remember, we defined this in terms of string, right? So if I do something like, let's say if you have a string, right, S to the power n. Okay, so this simply means what? This is n times, right? Now we are defining in terms of language, okay? So when I write L to the power n, what does that mean? So you basically combine, so you basically concatenate n words or strings from that language. Okay, so let's say, so that means, let's say the language has something like this, right? So let's just say there's something like this, okay? Let's just say A, B, C or something like that, A, B, C, A, or something like that. Okay, so that means you can, now you can start seeing the complexity, right? So if I do L to the power n, what does that mean? Or let's say L to the power 2, maybe L to the power 2. Let's just say 2, right? N can replace 2, right? So that means you have to choose what? Two different, not two different, even like you have to choose 2 words from your language, right? So you can choose AA, you can choose AB, you can choose BB, you can choose A and C, you can choose A then AA, right? Okay. So what I mean is, so what you can do, you can start with A, right? Then A, right? We can do A, B, right? Because this belongs to the language, this belongs to the language, right? Or you can do BA, you can do BB, right? You can do CA, AC, right? All this, or you can do A then AA, right? Remember, this is also a part of language, right? All right. Okay. So now you can kind of see the complexity, right? You can create all these different words in string, right? By using this simple set, right? Okay. Okay, so maybe you can write a simple program that basically does, given a set, okay, create all the possible words or strings, right? Okay, so now let's see. Okay, so maybe you can, okay, 11, 16. You have any class after this? Yes? Okay, let's stop. All right, so there are 2 more slides, so we can, what class is that? What class do you have after this? Oh, it's coming here? But what course is that? What course is that? Game programming, okay. Game programming, I don't know. Okay, so I'll stop here and then we